Okay, so the next thing that we want to revise is, of course, the notion of an electrostatic field. It's going to take me a while to write. Electrostatic field. So what is the characteristic of Coulomb's law that we are exploiting here? We are exploiting the fact that the force is linear in the charge that you are considering to test the value of your field. If you double your test charge, the force goes twice to it. Therefore, it's a kind of redundant thing for you to tell me the force for many, many different charges. You just need to give me one value, which I can then use to compute the force on any charge. And this handy value, of course, is the value of what we call the electrostatic field, which is an abstraction. We haven't seen it yet. We haven't met it yet. I'm at dinner with it. So it's an abstraction, okay? But later on, it will take on a real life. So the idea is that we rewrite the force acting on our test charge as the value of the test charge times the value now of a vector evaluated at the position of the test particle. So I write it like this. Okay. So again, of course, this is a fundamentally important thing. It's a trivial equation, which I know you know. I really know that you know this. However, once again, I want you to not forget the magic behind this equation, the absolutely non-trivial magic, in the sense that mathematically things could be very different. This is not a mathematical requirement. This is a physical fact. You could have a universe where this is absolutely not true here, and it would be just as easy to do mathematically. But where we live, that holds here. There is an object, the electrical field, and the reason why we call it a field, if you're not familiar with the word field, it's not, just a place where you grow stuff. The idea of the field is that it permeates all space. It's everywhere. It's a function of the coordinate that you have, and the coordinate that you have takes value in the physical space that you're considering. Okay? So this function here maps a coordinate in real space to a vector. Okay? It's a vector field. Vector field means vector valued field. Later we'll talk about scalar fields, vector fields. That's what these things mean. So the electrostatic field is a vector field. Okay, and that's its definition here. So of course you can just reuse the expressions that we had before. So say we have a set of oh, no green. Say we have a set of charges. Okay, a set of charges is going to create an E field at a certain position R in space, which is going to be just the linear superposition of the fields coming from all the individual source charges. So 1/4 pi epsilon 0, summation over all our source charges from 1 to n of just the R minus Ri divided by the distance R minus Ri. Yeah, and yeah, so cubed here. Okay, so here R has no subindex, so I can't use the accelerated notation here. But again, super important equation here. We're going, we're still at the trivial level here, but I once again really want to emphasize that this is actually full of physical content. Okay. Any questions on this? There's a very simple example in the notes, which I will actually let you do yourself. Or yes. Did I forget to put the charge? I forgot to put the charge. So there's a QI. Thank you very much. So there's QI multiplying that thing. Thank you. Squeezed in just at the last second. Okay, so let's do an example. So you've got a length here with what have I got? So I've got a charge Q here. I've got another charge Q here. The distance here between the two, we're going to call D. And I'm going to take the midpoint here, and we're going to go a height Z above this midpoint. And the question is to compute the electric field coming to that point here. Okay, so you can do that relatively easily. If you've got, call this angle here theta, then essentially if I take one of them, so the R minus R prime, so let this one be temporarily just this R prime, and then this R here. So that one there, it's just got this Z squared plus D over 2, well, D over 2 squared, so D squared over 4 square root. That's the distance. And essentially the cosine of the angle theta, because I'll be interested in projecting the force here back on the axis here, because of course the combination of these two here symmetrically will produce a force that goes completely in the vertical direction like this. Okay, and this cos theta is really just this essentially this Z over the R minus R prime. So essentially you can see that the field is just going to be given by this 1 over 4 pi epsilon 0, and I've got 2q times then the cos theta, so that gives me a Z divided by this Z squared plus D squared over 4 to the power of 3 halves. And in the Z hat direction, right? So Z hat direction is just the vertical direction, just the Coulomb's law, and then you just put it up like this.